Helo, Angel, Chopper, by any name you choose to call it, the helicopter has revolutionized the world of man-made flight. Although the helicopter was one of the earliest conceptions for power-driven flight, it was one of the latest to get into the air in practical form. In the 15th century, the great artist-inventor Leonardo da Vinci had analyzed the flight of birds and had made several sketches of an aircraft-like machine with lifting screws rotating about a central axis. In the 1900s, the Frenchmen Cornu and Breguet and Russian-born Igor Sikorsky were making their initial experiments with gas engines to turn the rotors. A dormant period followed. Then, in 1937, came dramatic news from Germany. The Fokker helicopter, whose performance was reported to be vastly superior to anything achieved so far. In 1939, Sikorsky, now in America, had built his famous VS-300 machine, the first to solve the problem of uncontrolled spinning or torque reaction by adding a small tail rotor. Thus began an age when helicopters were to play a most important part in both civil and military aviation. The helicopter's role in rescue work is already legendary. Large cities have employed helos manned by officers as an aid to law enforcement. Up-to-the-minute traffic advisories are broadcast to drivers to avoid traffic jams and expedite traffic flow during peak hours. Helicopters can move across difficult terrain to set towers, string and inspect transmission lines. The helo's powerful rotor wash can be used for more effective crop dusting. Or to save lives by blowing flames away from a blazing aircraft or building, allowing firemen and rescue personnel to move in close. Executives now travel door to door on business trips, the most important of these being our own chief executive, who often lands and takes off from the White House lawn. Navy helos operating with ASW task forces use sonar to search out enemy submarines. With this kind of underwater device, the helicopter can locate, then move in to attack and destroy any aggressor. The Vietnam conflict has been called the world's first helicopter war. Choppers have brought a new mobility to the battlefield. Troops, food, guns, and ammunition are quickly brought into battle. Gunships fly protection for ground forces. Wounded are picked up and quickly evacuated to hospitals. Unlike the fixed-wing aircraft, the helicopter has a unique freedom of movement. It can fly up or down, hover in place, fly forward or sideways, and can even fly backward. It can land without engine power in an area little more than its own length. How does this unique and versatile machine work? Although a complex machine, it flies for the same reason any heavier than air machine flies. Air passes over its airfoils to achieve lift. The airstream separates in front of the leading edge and moves across both the upper and lower surfaces. If we vary this angle at which the airfoil strikes the air, or its angle of attack, air passing over the top of the airfoil does not hug the surface as closely as air along the bottom. Both airstreams reach the trailing edge at the same time, but air along the top travels farther and thus must travel faster. This increase in velocity reduces the pressure on top of the airfoil. The result, a lift to the airfoil. The helo airfoil is not a fixed wing, but a series of two or more power-driven blades or wings, which revolve around a hub and is called a rotor. The action of the main rotor produces both the desired lift and thrust. Lift by increasing angle of attack on rotor blades, thrust by tilting the plane of rotation of the main rotor. The main rotor blades are attached to a shaft or mast connected through the transmission to the helicopter's engine. The mast is situated at or near the center of gravity in a single rotor helicopter. Helicopters are controlled about three axes: longitudinal axis, lateral axis, and vertical axis. There are four controls that enable the helicopter to move within these axes. In general, these are collective and throttle, rudders, and cyclic. Let's see how each of these control systems works in actual flight. The collective controls blade pitch and is connected to the blades by a mechanical linkage system. As we pull up on the collective, blade angle of attack is increased. However, this increased angle of attack offers more surface to the wind, creating greater drag. More power must be applied or blades will slow down. With additional power and increased angle of attack, the helo climbs. In gas turbine helicopters, a fuel control automatically compensates for this condition. In other types, the pilot must apply additional power manually. To increase altitude, we increase angle of attack, thereby increasing lift, assuming blade speed is constant. Conversely, to descend, we lower the collective. The blade now offers less angle of attack and consequently less lift. Therefore, the helo settles. Addition of collective will stop the descent. As the helicopter starts to rise, torque reaction begins to rotate the airframe. Torque reaction is the tendency of any rotational force applied in a specific direction to create an equal force in the opposite direction. Torque reaction is controlled by pressure on the rudder pedals, which govern the pitch or angle of attack of the tail rotor blades. Left rudder increases angle of attack. Right rudder decreases angle of attack. Suppose we are in a hover and we want to rotate left. As we apply light pressure on the left rudder pedal, the helo rotates left. The angle of attack of the tail rotor is increased, thereby overcompensating for torque reaction. To rotate right, we press the right rudder pedal. Angle of attack on the tail rotor blades is decreased, allowing partial torque reaction to rotate the helo. We are now ready to try horizontal or directional flight. This is accomplished by tilting the rotor. Control of the rotor's tilt is by the cyclic in front of the pilot. It controls movement about the lateral axis, forward or backward, and also about the longitudinal axis for right or left turns while in forward flight. The cyclic activates a series of linkage leading to the lower of two circular metal plates, one above the other, separated by bearings. The entire mechanism is called a swash plate assembly. The lower or stationary swash plate does not revolve, but can be tilted in any direction by movement of the cyclic control stick in that direction. This tilts the upper or rotating swash plate, which revolves about the shaft, changing blade pitch as the blades rotate. Directional control is achieved by two simultaneous actions: tilting the rotor in the direction we wish to go and changing the pitch of the tail rotor. From a hover, forward flight is achieved by moving the cyclic forward. You will notice that the helo tends to settle due to loss of ground cushion. An increase in the collective must be made to maintain constant altitude. To make a right turn during forward flight, move the cyclic slightly to the right. At the same time, press gently on the right rudder pedal, decreasing the angle of attack of the tail rotor. To turn left, reverse direction of these movements. Smooth, positive control will result in a perfectly coordinated turn. Upon reaching the desired heading, neutralize controls. To fly sideways from a hover, move the cyclic in the desired direction, while maintaining constant fuselage heading by rudder pedal action. As we have seen, collective pitch changes angle of attack and controls vertical lift to allow the helicopter to fly up, down, or to hover. Rudder pedals operate the tail rotor, which aids in directional control of the aircraft. The cyclic controls forward, backward, or sideways motion by tilting the rotor disc. One question often asked is, what happens if the engine fails? The answer is autorotation. A freewheeling unit disengages the rotor system. Immediately lower the collective to reduce angle of attack. This will lessen drag and aid in maintaining rotor RPM. During autorotation, as the helicopter begins to lose altitude, air passes upward through the rotor system, forcing the blades to continue rotating in the same direction. Rotor RPM will be about the same as when your helo is flying under power. Establish and maintain designated autorotation airspeed. At the prescribed height above touchdown point, assume a landing attitude. Pull up smoothly on the collective, reducing your rate of descent by turning the potential energy of the rotating blades into lift. There is now a downward flow of air through the rotor, which allows a safe and gentle landing. Your vertical rate of descent without power will be roughly comparable to that of a parachute. From a hover at altitude, a helicopter needs approximately 400 feet to pick up sufficient forward speed to effect a safe landing. However, at cruising speeds, effective autorotation can be obtained at nearly any altitude. When the engine stops at these speeds, air velocity forces air back through the rotor system almost immediately, thus permitting a safe landing from almost any altitude. Now to review what we have learned about helicopter flight. There are three kinds of flight: vertical flight, hovering, and horizontal flight. Changing the pitch or angle of the main rotor and tail rotor blades controls helicopter movements. In vertical flight, the collective controls the magnitude of thrust. To climb, all blades are at high pitch. To hover, all blades are at medium pitch. To descend, all blades are at low pitch. In horizontal flight, the cyclic controls the direction of thrust and is moved in the desired direction of travel. Rotation of the helo is controlled by changing the pitch of tail rotor blades. Although this film has covered the operation of the single lifting rotor, these basic principles also apply to other configurations. The other three have no tail rotor. Torque is offset by a second rotor spinning in the opposite direction. These are tandem with rotors in front and rear. It is insensitive to load distribution. The Syncropter helicopter, which has intermeshed blades, synchronized as in an egg beater. The coaxial helicopter has twin rotors on the same shaft, mounted one over the other, whirling in opposite directions. Another single rotor helo configuration is the rigid rotor. It is stable, quick to respond, and more maneuverable. It is fast becoming a part of our growing helicopter force. You may be searching for enemy submarines on ASW missions. Flying vertical replenishment. Rescuing astronauts from the sea. airlifting troops in a vertical envelopment opposing enemy forces. Whatever your job, you will be a part of an expanding professional helicopter force.